first thing I'd like you to do is on that back page of your graph paper. You did all the data collection on the front page. It's got your research question and your weights and your mass. You should have like 10 to 12 data points. Now we're going to flip on the back page and use that spot to graph. So I'd like you to orient that graph paper so it's landscape style, and that'll give us the largest graphical area that we can use so that we can really see a trend. When you go to sketch in your axis, you want to make sure that you leave some room for the labels, but you also want to give as large of a graphical area as possible. So maybe I'll take up most of the graph paper, something like this. The next step is you just want to label your axes, and we had weight and mass. Weight was our dependent variable, and the way we stated it is weight depends on the x-axis, or the independent variable. So we'd say weight for the variable, and then the unit of weight was in newtons, and you can just leave the symbol for newtons. On the x-axis we had mass, and the unit for mass that we measured in was grams. We'll talk a little bit later, the actual standard unit is the kilogram, but we collected all our data in just grams. Once you have that done, now we have to start scaling this out so it makes sense. A consistent scale is super important in physics, and it's often something that gets missed. If you look at our data table, let's kind of move it where we can see it. On the y-axis, I need to pick values that at least can include a small number like 1, and maybe my highest number somewhere up around like 19 or 20. So I could just go by ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 20. But it's really up to you. The point is that you want to pick something that consistently stretches out that scale so that 20 will end up, the higher range will end up being all the way at the top of the graph, and then the lower numbers, 0, will be all the way at the bottom. So I'm deciding that I'm going to represent a few blocks at a time, maybe like every 4 blocks equals 2 actual units of newtons. So again, you'll be more precise because you can actually count the number of squares, but I'm just kind of eyeballing it to make it look like it'll show up. So like 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now you don't have to, like, you can see how I did that there. I didn't label every single number along the way. If you want to, that's fine, or if you want to just kind of make tick marks and then label every couple, that is okay as well, just as long as it looks nice and neat along that axis. Now the next big thing that we got to have down is that we don't have to jump by the same numbers along the x-axis that we did on the y-axis. So even though I went every 2 on the y, that doesn't mean I have to use that same scale on the x. You use an appropriate scale for the x. If I went by 2s on the x, my highest number I have to get up to is 1800. Well, that is going to be an incredibly large amount of tick marks if I went by 2. So I'm not going to go by 2s, that would be kind of ridiculous. Maybe I can go by 200s or 400s, something else to make that spread out, but I just want you to be aware that you don't have to go by the same scaling. So if I tried to stretch that out, maybe 200, 400, 600, 800, 1,000, 1,200, 400, 600, 800. Something like that would space that out nicely. And then again, just kind of only labeling a few of them just so it's not as much information crammed in there. If I labeled every single one, it'd be really hard to see what I was writing. I'm just kind of writing the every other data point in that. Alright, so once I have a labeled graph and it's consistent, then I want to just start plotting my points, and I just transfer those onto the graph, and hopefully as long as we've scaled right, it'll plot a nice relationship for us. On this first data point, it's 1.2, and that corresponds with 100 grams. Well, I don't have those hash marks actually on there, so this is where I'd have to use the divisions in the graph paper to kind of best estimate. So halfway between 2 and 0 would be 1, so that data point's going to be about there, and then halfway between 200 and 0 would be 100. So that first data point is going to be somewhere about there. And you'll have to do this process for the data points that aren't falling directly on hash marks, and that's totally fine. If you can get it as close as possible, the trend should show up. Right, so I've skipped ahead and just kind of plotted the rest of what was on my beginning data table, and yours will have a lot more data points filled out. But one thing I want to point out to you is that don't worry if your data doesn't perfectly line up. You can see a couple of these are, they're kind of zigzagging back and forth, even if it's like really far off, like you're kind of getting this scatter going on. The point is that after you plot the data as it is, you look for your best average trend line. And so when we put a trend line on there, then you're looking for it to cut through the majority of the data. It's a line that averages out your data. So it doesn't necessarily have to cut through every point. In fact, a lot of times it won't cut through all the points. But you're looking for something that would be the overall average of your data. So you see how mine doesn't actually go right through 0, 0. This trend line would be the best average of all that data, the overall trend that I'm seeing. And don't just force it to go through 0, 0 because you think it should. If yours happens to all line up right along the line, that's great. But don't just make it happen that way all the time. You can see, like, if I put mine through 0, 0, that doesn't really represent this data out here. Now I'm kind of leaving this stuff out, and I'm not averaging as close to that as I can. So just be careful about that when you pick an average trend line. But this line is going to become our function that we'll write our equation off of, and that's what we'll work on next. All right, now we're ready to write the function of our line. And if you have some open space, just like on your graph, you could squeeze the equation in there and just kind of like box around it when you're done. But we always want to finish a graph in physics with a trend and know the slope and the y-intercept. All those values are going to become important to understand what's going on. So let's just start with what the general form of any line is. Our equation for any line is y equals mx plus b. That's a math way of talking about it. In physics, we don't want to use these variables because we didn't graph y's, we didn't graph x's, we graphed weight and mass. So we swapped those variables out for the actual variables that we used in the graph. So if I was going to rewrite this, that would be the weight of the object is equal to some slope value, I'll come back to that in just a second, multiplied by mass plus b. The b term, remember, is just our y-intercept. So I'm going to estimate that y-intercept. It's not really at 2. It seems to be just below 2. So I'll say about 1.6 newtons. Now, slope. I have found that students struggle with slope, and something that just coming from your math class, I think you get bogged down too much in the formula of slope. If you remember this, they taught you m equals y2 minus y1 over x2 minus x1. And if that works for you and you're good with that, great. I think of slope more simply as just how much you have to go up and how much you have to go over to hit the line. Or if it was a downward line, how much you have to go down and how much you have to go over. But when you just think about it as I'm starting here on the graph and I'm going to go up a certain amount and over a certain amount to hit the graph again, then I'm really only paying attention to that change in the y divided by the change in the x. So that formula represents that. But if you can just get that conceptually down, we can do slope calculations much quicker than finding coordinate pairs and then subtracting out the points. So what I would suggest is pick points that are easy. You don't just go for data points that show up. You have to make sure that you pick 2 points along the line. So I look for where the line crosses like graph paper, where the line would be right in a major intersection, so I can just use my grid lines and follow it up. Maybe there was one right at 1400, and then trace it over and it lined up with this 16. So 1416, and I would use that as one of my points. So pick any 2 points along the line and do your slope calculation. Again, I think it's more simple to just go how much up divided by how much over. but finish out that calculation and put it in there. So let's say after doing a calculation, I got that my slope, I plug in my coordinates here and I get a value of 0.0097 for a slope. I don't just want to put that straight up number into that formula. I need units with that because on my y-axis I took newtons and I divided by a separate quantity. I didn't just divide by newtons. Again, I divided by grams. So you have to keep track of that in that number. That number needs those units to go along with it to accurately represent what just got divided. So I would need to finish that with having newtons divided by grams. So this value of slope, 0.0097 newtons per gram, that will become what I plug into this. So I finish off my math model. I'm going to write it one more time. It would just say that the weight of the object is equal to 0.0097 newtons per gram times mass plus 1.6 newtons. This formula is what we'll call a math model. It models what's happening with our trend in data. And yes, it is really just a y equals mx plus b equation, but you can see this clearly isn't just showing up as y, mx, and b. We want to swap out what we actually measured. So weight for y, mass for x. Our slope, you see, has the units of what we divided, newtons per gram, and then the y. So what does our slope mean? That's really the most important thing out of this lab. And so I want you to take a look at this math model again. This is just some sample data that I've been using. And the slope here says it's 0.0097 newtons per gram. Well, in a sentence, so we get a little bit more context to that, it says for every 1 gram of matter, every 1 gram would feel 0.0097 newtons of force. And that force is coming from the force of gravity. So it's like the Earth pulls on every gram of matter with a strength of 0.0097 newtons. Now, the gram is not the standard unit, and so if we do a little conversion here and make that newtons per kilogram, that would be the standard. We end up with a value that's about 9.7 newtons for every kilogram of mass. Well, you've probably heard that amount before. 9.7 newtons for every kilogram of mass is really close to 9.8 newtons for every kilogram of mass, and that is in fact the field strength here of Earth. So the gravitational field strength is this value. It has a symbol of lowercase g, and it just tells us how strong the Earth pulls every kilogram of matter here on that planet. For Earth, we get 9.8 newtons of force of gravity for every kilogram of matter, but if you go to other planets, you will have different amounts. So it really shows you that the weight of the object is dependent upon that field strength. And the reason that we get away with mixing mass and weight here on Earth is because that field strength is always the same value. We always use 9.8 newtons per kilogram here on Earth. But in reality, it's just a calculation combined with mass that gives us the amount of force. So all this leads us to this equation then. If you generalize your math model is very specific to your set of data. So your numbers, your y-intercept, your actual slope, it's because of your particular lab setup. Maybe your device had some systematic errors in there of friction when it was being pulled on, or even how much you estimated values that make your math model very specific to your setup. We can generalize your math model, though, into an overall equation that we can start using. And the overall equation then says, if you compare the force of gravity, which is weight, to the amount of mass, which is just the matter in the object, then they will relate to each other by a factor of the field strength. So your formula says weight equals the field strength times mass. That's how we can calculate the amount of weight that an object has. And you'll often see this rearranged where the slope comes after mass, and so they'll write the equation as the force of gravity equals mg. Now, that formula doesn't convert mass to force. it calculates force off the principle of mass and field strength. That's an important distinction to make, that we don't just convert from mass to force, that the force of gravity is a calculatable amount when you take into account the mass of the object and the field strength that it experiences here on Earth. That is our first equation that we've derived in AP Physics, and then we will follow that up with a video assignment to finish off this lab.